Okay, folks, decided to make one short video on gas zone porosities. And we've got a little friend over there. Oh, sorry, the wrong hand, this one. There he is, look, see? He's very interested in gas zones, so I think you'll be interested as well. Oh, that's if you're a keen petrophysicist, that is. Okay, now, yeah, gas zone processes are actually quite difficult. Gas zones are quite difficult to evaluate with logs because they affect all the porosity logs quite dramatically. Of course, the most famous effect is the positive crossover that you get with a good porosity gas-filled zone, because it makes the density very light and it makes the neutron appear to be very low porosity, so you get this big separation. But the best method with core that I've found, and it really is, I mean, I've tried many methods. I've probably tried maybe 30 different ways of getting good porosities, and particularly good gas zone porosities, over the many years that I've been doing, quite detailed petrophysics. And the best way I've found is this density neutron and core cross plot method. So what you do is essentially, I'll show you a slide in a minute, but basically what you do is, where you've got a bit of a chord interval, and of course we don't always have chord, but where you do have a bit of chord interval, then you can reverse calculate from the core the required apparent fluid density that you need to make that density log give you your core porosity. And I'm calling that rho fluid apparent core. So rho F A core. Okay, and then that's the value that if you put that value in the density porosity equation, it will give you, that's the value for fluid density that will give you the core porosity, because you reverse calculate it from the core porosity, right? Okay, so what we do is we see what that required value for fluid density is, and then we cross plot it with a log parameter. Guess what log parameter we cross plot it with? Well, what log parameter is strongly controlled by the fluid density? Any answers? Density neutron separation, the one I've just been talking about. The lighter the fluid density, the bigger the separation you get, right? The bigger the positive separation you get. So why not, first of all, determine exactly what rho fluid you need to make the density log give you your core porosity, and then simply correlate that with the density neutron crossover, which is dominated in fact by the fluid density. So that's what I've done in this cross plot here, and that's what I always do now. I always use this little method, which I shall show you about over here. Okay, there we are. There we go. That's the little cross plot. So we've got on the y-axis, sorry, we've got the apparent fluid density from the core, and that's the density porosity equation, solving for rho fluid, right? So I've used that porosity in there that I'm telling the density log to match that core porosity there, right? And that's the fluid density that gives it, that makes that rho B give you your core porosity. That's on the y-axis, and on the x-axis is the neutron density separation, which I call SEP-ND. That's my convention to call it SEP-ND, separation neutron density. That's on that axis, and then you make a cross plot, and you find a relationship between the separation from the log data and the required fluid density, and you've got a little equation that gives you a fluid density. And when you put that equation into your fluid density, and density porosity equation, you get a very good, the best match, in fact, that I've found for porosity from logs. And then, of course, if you've got normalized logs where you've got a consistent data set across the field, you can use that equation to drive the porosity in all the other wells. Now, the marvelous thing about this method, well, one of the marvelous things about it, is that it actually can be used across different fluid zones. Now, as you may know, if you're a sort of reasonably experienced petrophysicist, one of the main complaints with the density neutron, with the density method for deriving porosity, is that you have to keep getting different fluid parameters for each fluid zone that you're in, right? So for example, if you're in a water zone, obviously the row fluid would be different to if you're in a gas zone, wouldn't it? It would be heavier, wouldn't it? So, but if you use this method, if you use this marvelous cross plot method, then we can see that automatically accounts for itself, doesn't it? It automatically deals with that, because as you go into a water zone, you get less density neutron separation, and because you get less density neutron separation, the fluid density is calculated as a different value, a value which is more like a water density value and fluid density value, and then you will get the correct. It will still, even if you go through multiple fluid zones, for example in a stacked shaly sand where you may have countless fluid zones, water, oil, gas, water, gas, gas, water, etc. This thing is automatically giving you the right fluid density, because the separation is driving it. Okay, that's all I wanted to say about that. There are, of course, other methods for gas zone. The famous one perhaps is let's get my cursor down here, is the shell method, which is just iterating the density and the SXO parameter, which I don't actually like. I mean, it's a nice little neat method, but actually I don't think it works very well in real life. It's one of these shell ideas that is popular, but I don't think it's particularly good myself. But it is used quite widely, and the good a good method is the traditional log analysis, which is just basically density neutron porosity, but it's this variant of that, which is the sum of the squares of density and neutron porosity divided by 2 and the square root taken of that. So that is slightly matches core porosity better than just the average of density neutron. Because if you think about it, what's happening is that the term which is biggest here, and in gas zones that's slightly bigger than this one, right? In fact, it's a lot bigger than that one. That will dominate, because it's squared, it will actually have a bigger effect on the porosity than that one. And that's what we usually find, that the gas zone porosities are slightly closer to the density porosity than the neutron porosity. So not just the average, but slightly nearer the density. And that's what this equation is really doing. Can you see that? Okay, anyway, that's enough of that. I think that's a nice little summary, and try to remember, when you've got core, use the apparent fluid density from the density neutron crossover. You'll find that it's very useful, and of course you can tell your customers, you can tell your clients that this is a core-based porosity, because of course you are referencing core to get your apparent fluid density there. Okay, enough.